the sun's pull is weakening, not because gravity is changing, but because the sun is. Our star is losing mass continuously, and that loss is altering the structure of the solar system in real time. The effect is tiny, but it accumulates, which means something we assumed was permanent isn't. And that's why astronomers are quietly going back to the numbers. The mass of the sun is one of the most important numbers in all of astronomy. It serves as the baseline for measuring other stars. When astronomers say a star has a mass of 0.5 solar masses, or 3 solar masses, they're using the sun as the unit of comparison. It's the cosmic yardstick, the reference point. And for most purposes, we've known the sun's mass to remarkable precision for over a century. But here's the problem. We can't actually measure the sun's mass directly. You can't send a probe into the sun's core to count atoms. Instead, we infer the sun's mass from its gravitational effects on other objects, specifically on the planets that orbit it. The method goes back to Isaac Newton. In the late 1600s, Newton derived his law of universal gravitation, which states that the gravitational force between two objects depends on their masses and the distance between them. From this, you can calculate the mass of a central body like the Sun if you know the orbital period and distance of something orbiting it. We don't need to know the Sun's mass to 10 decimal places. We just need to know it well enough to predict planetary motion, plan spacecraft trajectories, and understand stellar evolution. Except now, something has changed. The planets aren't moving quite the way they should. And the question is the sun's mass changing, or is something else going on? To answer that, astronomers turned to a tool called planetary ephemerides. These are computational models that predict the positions of planets over time, based on the best available data about their orbits, masses, and the forces acting on them. The most sophisticated ephemerides like the EPM series developed in Russia or the DE series from NASA's Jet Propulsion Laboratory incorporate decades of observations, including radar measurements, spacecraft tracking data, and even historical records of eclipses and planetary transits. In the early 2000s, researchers at the Institute of Applied Astronomy in Russia began analyzing data from a new version of their planetary ephemeris called EPM 2010. They were looking for small corrections, tiny adjustments that would make the model match observations more precisely. And they found something unexpected. The best fit to the data required a decrease in the sun's gravitational parameter. A tiny decrease, roughly -5 parts in 10 trillion per year, but a decrease nonetheless. At first, this was just a number in a computer model, a correction factor. It didn't necessarily mean the sun was losing mass. It could have been an artifact of the data, or a sign that the gravitational constant itself was changing over time, a possibility predicted by some alternative theories of gravity. But as the measurements improved, and as newer versions of the ephemerides were developed, EPM 2017, EPM 2019, the result held. If anything, it became more certain. By the time astronomers published their findings in the journal Astronomy and Astrophysics in 2021, the evidence was clear. The sun's gravitational parameter was decreasing at a rate of roughly -10 parts in 10 trillion per year. And the most likely explanation was not a change in the gravitational constant, but a change in the sun's mass. The sun was losing weight. The sun is not a solid object. It's a sphere of plasma superheated gas so hot that electrons are stripped from atoms, creating a roiling ocean of charged particles held together by gravity. At the core, temperatures reach 15 million degrees Celsius. That's hot enough to fuse hydrogen atoms into helium, releasing enormous amounts of energy in the process. This energy radiates outward, eventually reaching the surface, where it escapes into space as light and heat. But energy is not massless. According to Einstein's equation, energy equals mass times the speed of light squared. Every photon of light that leaves the sun carries a tiny bit of mass with it. Not literal mass in the form of particles, but an equivalent amount of mass energy converted from matter in the core through fusion. This process is called radiative mass loss, and it's one of the two main ways the Sun is losing mass. The numbers are staggering. Every second, the Sun converts approximately 4 million tons of matter into energy. That energy radiates outward as light, neutrinos, and other forms of electromagnetic radiation. Over the course of a year, this amounts to a loss of roughly 1.3 times 10 to the power of 20 grams. That's about 1/30 millionth of the Sun's total mass. It sounds like a lot, and in absolute terms, it is. But relative to the Sun's total mass, about 2 times 10 to the power of 33 grams, it's infinitesimal. A loss of 1 part in 10 trillion per year. And that matches, almost exactly, what the planetary ephemerides are telling us. But there's a second source of mass loss, one that's harder to measure and more variable over time: the solar wind. The solar wind is a stream of charged particles, mostly protons and electrons, that constantly flows outward from the Sun's corona. It's not like the radiation we see as sunlight. It's actual matter, plasma, and it's being ejected into space at speeds of several hundred kilometers per second. The mechanism behind the solar wind was first proposed by physicist Eugene Parker in 1958. He argued that the Sun's outer atmosphere, the corona, is so hot that gravity can't hold it down. The gas expands outward, creating a continuous flow of material that streams past the planets and out into interstellar space. At Earth's orbit, the solar wind is relatively tenuous, only a few particles per cubic centimeter, but it's moving fast. And over the entire surface area of a sphere centered on the Sun and passing through Earth's orbit, the total mass loss adds up. The exact rate of solar wind mass loss is difficult to measure. It varies depending on solar activity. During periods of high activity, when the Sun has lots of sunspots and produces frequent flares, the solar wind can be much stronger. During quiet periods, it's weaker. But on average, the solar wind carries away about 1 to 2 million tons of material every second. That's roughly half the mass lost through radiation. Combined, these two processes, radiation and solar wind, account for a total mass loss rate of approximately -7 to -13 parts in 10 trillion per year. Again, that matches the observational data. But there's a complication. The Sun is also gaining mass. Not much, but some. Every day, small particles of dust, meteoroids, and the occasional comet fall into the Sun, adding material back to its mass. The exact rate of this infall is uncertain, but the best estimates suggest it's on the order of 1 part in 10 trillion per year. Positive, offsetting a small fraction of the mass loss. When you add it all up, radiation, solar wind, and infall, the net mass loss rate of the Sun is roughly -10 parts in 10 trillion per year. And that's exactly what the planetary ephemerides are measuring. So the mystery is solved, right? The Sun is losing mass because it's radiating energy and blowing off plasma. The planets are drifting outward in response. Everything makes sense, except for one thing. If the Sun has been losing mass at this rate for the past 4.5 billion years, its entire lifetime, then it has lost about 1 part in 3,500 of its original mass. That's not much, but it's not nothing. And over that timescale, the orbits of the planets should have shifted by measurable amounts. So astronomers started asking, has the Sun always been losing mass at the same rate, or has the rate changed over time? The Sun is not the same star it was 4.5 billion years ago. When the Sun first formed, it was cooler, dimmer, and less massive than it is now. No, wait, that's not quite right. It was cooler and dimmer, yes, but less massive? Here's the paradox. The Sun's luminosity, the total amount of energy it radiates, has increased over time. Early in the Sun's life, it was only about 70% as bright as it is today. This is called the faint young sun problem, and it has profound implications for Earth's climate history. If the Sun was that much dimmer, Earth should have been frozen solid for most of its early history. But geological evidence shows that liquid water existed on Earth's surface as far back as 4 billion years ago. So either Earth's atmosphere was much thicker and more insulating back then, or something else is going on. But here's the key point. As the sun has gotten brighter, its mass loss rate through radiation has also increased. A brighter sun radiates more energy, and more energy radiated means more mass lost. So the sun has been losing mass faster over time, not slower. That complicates the picture, because it means we can't just extrapolate the current mass loss rate backward in time. The rate has changed. And to understand how the planet's orbits have evolved, we need to model that change. In 2021, researchers published a detailed study on this exact question. They used numerical simulations to track the evolution of planetary orbits over the sun's lifetime, accounting for the time-varying mass loss rate. And they found something interesting. Over the past 4.5 billion years, the planets have drifted outward by a small but measurable amount. Earth's orbit, for example, has increased by roughly 15,000 kilometers. That's about 2% of the Earth-Moon distance. Not enough to significantly affect Earth's climate, but enough to show up in high-precision measurements of ancient geological cycles. And there's another way to test this. Ancient fossils preserve records of Earth's orbital parameters, things like the length of the day and the distance to the Moon, going back hundreds of millions of years. By comparing those records to predictions from orbital models, astronomers can check whether the sun's mass loss rate has been consistent with what we observe today. So far, the data matches. The sun's current mass loss rate, extrapolated backward in time with corrections for its increasing luminosity, is consistent with the geological record. But what about the future? The sun's mass loss rate won't stay constant. In about 5 billion years, the sun will exhaust the hydrogen fuel in its core and begin fusing helium. When that happens, it will expand into a red giant, swelling to hundreds of times its current size. During that phase, the sun's outer layers will become much less tightly bound by gravity, and the solar wind will strengthen dramatically. In fact, during the red giant phase, the sun is expected to lose about 30 to 40% of its total mass. That's a staggering amount, and it will have dramatic effects on the planets. As the sun loses mass, the planet's orbits will expand. By the time the sun reaches the tip of the red giant branch, Earth's orbit will have moved outward by roughly 40 to 50%. Mars will drift even farther. The outer planets, Jupiter, Saturn, Uranus, Neptune, will also move outward, though by smaller percentages because they're already far from the sun. But there's a catch. Some planets won't survive. Mercury and Venus are likely to be engulfed by the expanding sun. Earth might survive, but it will be scorched. The oceans will evaporate. The atmosphere will be stripped away. By the time the sun settles into its final phase, a white dwarf, slowly cooling over trillions of years, Earth will be a barren, lifeless rock, orbiting at a distance roughly equivalent to where Mars is today. And that raises a final question. If the sun's mass loss has such profound effects on the planets, and if we can measure those effects with high precision, then why are astronomers rechecking the sun's mass now? What changed? The breakthrough came from an unexpected place. Not from observing the sun directly, but from watching Mercury. Mercury is the closest planet to the sun. It orbits at an average distance of about 58 million kilometers, less than 40% of Earth's orbital distance. Because it's so close, Mercury feels the sun's gravity more strongly than any other planet. And that makes it an ideal laboratory for testing theories of gravity. In the early 20th century, astronomers noticed something strange about Mercury's orbit. The point of closest approach to the sun, called the perihelion, was slowly rotating around the sun. This phenomenon, called perihelion precession, had been observed for other planets as well. But Mercury's precession was faster than Newton's laws of gravity could explain. The discrepancy was tiny, only 43 arcseconds per century, but it was consistent, and it couldn't be explained by the gravitational pull of the other planets. In 1915, Albert Einstein solved the mystery. His theory of general relativity predicted that space-time near the Sun would be curved, and that this curvature would cause Mercury's perihelion to precess by exactly the amount that had been observed. It was one of the first major confirmations of general relativity, and it solidified Einstein's place in the history of physics. But here's the thing: general relativity doesn't just predict perihelion precession, it also predicts how the Sun's mass affects the curvature of space-time. And if the Sun's mass is changing, then that curvature is changing too. So, in the early 2000s, when NASA launched the Messenger spacecraft, short for Mercury surface, space environment, geochemistry, and ranging, one of its goals was to measure Mercury's orbit with unprecedented precision. Not just to study Mercury itself, but to test general relativity in the strongest gravitational field available in the solar system. Messenger entered orbit around Mercury in March 2011. For the next 4 years, it mapped the planet's surface, studied its magnetic field, and tracked its position with extreme accuracy using radio tracking from Earth. And what it found was remarkable. By the time Messenger's mission ended in April 2015, astronomers had enough data to measure Mercury's orbital parameters, including perihelion precession, to a precision far beyond what had been possible before. And they used that data to test general relativity more rigorously than ever before. The result? General relativity passed the test. But the data also revealed something else: a small, systematic deviation in Mercury's orbit that couldn't be explained by general relativity alone. The deviation was consistent with a decrease in the Sun's gravitational parameter, the same decrease that had been detected in the planetary ephemerides. This was a crucial confirmation, because Messenger's data came from a completely independent source. It wasn't based on radar measurements of Venus, or historical records of lunar eclipses, or any of the other data used to build the planetary ephemerides. It was based on tracking a spacecraft in orbit around Mercury, and it gave the same answer. The Sun's mass is decreasing, and the rate of decrease matches the predictions from radiative mass loss and solar wind. But Mercury's orbit isn't influenced by the Sun's mass alone. The Sun is not a perfectly smooth, spherical object. It rotates, it bulges slightly at the equator, and its interior is constantly shifting. That uneven mass distribution subtly alters the Sun's gravitational field, adding a small extra effect to Mercury's motion. On its own, the effect is tiny. But at the level of precision reached by Messenger, it becomes impossible to ignore. To isolate the Sun's mass loss, astronomers first have to model the Sun's shape and accept that it isn't perfectly constant. That means every measurement of Mercury's orbit carries an additional layer of uncertainty, not enough to make the signal disappear, but enough to remind scientists that even their most precise confirmations rest on assumptions that are still being refined. And even that shape isn't fixed. The Sun's magnetic field rises and falls over its activity cycle, subtly changing how different layers of the Sun rotate. Over time, that alters the Sun's shape just enough to matter at extreme precision, which means the Sun's gravitational field isn't just uneven, it's variable. But Messenger's data did something else too. It allowed astronomers to place tighter constraints on the gravitational constant itself. Because if the Sun's mass is decreasing, and we can measure that decrease with high precision, then we can also test whether the gravitational constant is changing over time. In Einstein's general relativity, the gravitational constant is exactly constant. It doesn't change. But some alternative theories of gravity, like scalar tensor theories or certain versions of quantum gravity, predict that the gravitational constant might vary over time. If it does, then the product of the gravitational constant and the Sun's mass could be changing for two reasons: a decrease in the Sun's mass and a change in the gravitational constant itself. To separate those two effects, astronomers need to measure both quantities independently, and that's extremely difficult. But Messenger's data, combined with the planetary ephemerides, allowed them to place limits on how much the gravitational constant could be changing. The result? Any change in the gravitational constant must be extremely small, less than about 5 parts in 10 trillion per year. and possibly zero. That's an important result, because it means that, to the limits of current measurements, general relativity is correct. The gravitational constant is constant, and the Sun's mass loss is the primary driver of the observed changes in planetary orbits. But there's still uncertainty, and that's why astronomers are going back to recheck everything. And at this level of precision, even time becomes part of the measurement. Astronomers don't track planetary motion using Earth's rotation, but a relativistic timescale defined by the solar system itself. That timescale assumes gravity behaves exactly as our best theories predict, which means every attempt to measure the Sun's mass is also, quietly, a test of the framework used to define time in the first place. As of 2025, here's what we know. The Sun's mass is decreasing. The rate of decrease is approximately -10 parts in 10 trillion per year. That's equivalent to losing about 4 million tons of matter every second through radiative mass loss and solar wind combined. This rate has been measured using multiple independent methods: planetary ephemerides, spacecraft tracking data from MESSENGER, observations of Mercury's orbit. All of them give consistent results. We also know that this mass loss is not uniform over time. The Sun's luminosity has increased over its lifetime, and so has its mass loss rate. Early in the Sun's history, it was losing mass more slowly. In the future, when the Sun becomes a red giant, it will lose mass much more rapidly. We know that the gravitational constant is not changing, or if it is, the change is smaller than about 5 parts in 10 trillion per year. That's consistent with general relativity, which predicts that the gravitational constant should be exactly constant. We know that the Sun's quadrupole moment, its deviation from a perfect sphere, is about 2 × 10⁻⁻⁷, and that this value varies slightly over the solar cycle. But these variations are small enough that they don't significantly affect the measured mass loss rate. And we know that relativistic effects, perihelion precession, the Lense-Thirring effect, the Shapiro delay, are all consistent with general relativity to the limits of current measurements. So the mystery is solved, right? The Sun's mass is decreasing because it's radiating energy and blowing off plasma. The planets are drifting outward in response. We've measured it. We've confirmed it with multiple methods. And it all makes sense. Except for one thing. Why are astronomers still rechecking the numbers? Here's the uncomfortable truth. Even though we've measured the Sun's mass loss rate to high precision, there are still uncertainties. And those uncertainties matter. The largest source of uncertainty is the solar wind. Unlike radiation, which is relatively constant and predictable, the solar wind is variable. It fluctuates on timescales of days, months, and years. And we don't have continuous, high-resolution measurements of the solar wind over long periods. Most of what we know about the solar wind comes from spacecraft that have orbited or passed through the inner solar system. Missions like Ulysses, which orbited the Sun from 1990 to 2008, or the Parker Solar Probe, launched in 2018, which is currently making close approaches to the Sun, diving through the corona to measure the solar wind near its source. But even with these missions, we're still sampling only a small fraction of the solar wind. We're measuring it at specific locations, at specific times. And then we're extrapolating those measurements to estimate the total mass loss over the entire surface of the Sun, averaged over years or decades. That extrapolation introduces uncertainty. And that uncertainty propagates into the estimates of the Sun's total mass loss rate. Currently, the uncertainty in the solar wind contribution is about ±30%. That might not sound like much, but it corresponds to an uncertainty of about 2 parts in 10 trillion per year in the total mass loss rate, which is roughly 20% of the measured value. So even though we know the Sun is losing mass, we don't know the exact rate to better than about 10 to 20%. And that matters for several reasons. First, if we want to predict how planetary orbits will evolve over millions of years, we need to know the mass loss rate accurately. A 20% uncertainty in the mass loss rate translates into a 20% uncertainty in how much the planet's orbits will expand. For Earth, that's a difference of several thousand kilometers, which could be important for understanding long-term climate cycles or for planning future space missions. Second, if we want to test whether the gravitational constant is changing, we need to separate the effects of mass loss from any potential change in the constant itself. And to do that, we need to know the mass loss rate to better precision than we currently do. Third, there are other processes that could contribute to the Sun's mass balance. Things like the infall of comets and asteroids, or the ejection of material during coronal mass ejections, or even more exotic processes, like the possible emission of dark matter particles from the Sun's core. Most of these effects are expected to be very small, but we can't rule them out entirely without better measurements. So astronomers are working to improve the data. New missions, better models, more precise tracking of the planets and spacecraft. And they're re-examining old data, looking for subtle effects they might have missed. The Sun's mass loss doesn't stop with the red giant phase. After the Sun exhausts the hydrogen in its core and then the helium, it will shed its outer layers, creating a planetary nebula. What remains will be the Sun's core, a hot, dense object about the size of Earth, composed mostly of carbon and oxygen. This is a white dwarf, and it will contain only about half to 60% of the Sun's original mass. The rest will have been lost to space, carried away by the intense stellar winds of the red giant phase. And this will have dramatic effects on the planets. As the Sun loses mass, the planets will drift outward, but not all of them will survive. Mercury and Venus will almost certainly be engulfed during the red giant phase. Earth's fate is uncertain. Some models predict it will be engulfed. Others suggest it will barely escape. Mars and the outer planets will survive, but they will be in much larger orbits. Jupiter, for example, will drift outward from about 5 astronomical units to about 8 or 9 astronomical units. Saturn will move from 10 to about 16 astronomical units, and so on. But here's the interesting part. Once the Sun becomes a white dwarf and its mass stabilizes, the planets will no longer drift. Their orbits will become stable again, and those orbits will be much larger than they are today. This has implications for the search for planets around white dwarfs, because if other Sun-like stars go through the same process, then any planets that survive the red giant phase will be orbiting their white dwarf hosts at large distances that are difficult to detect with current methods. But there's another possibility. What if some planets don't survive? What if, during the chaotic period of mass loss, planets get ejected from the system entirely? This is not just speculation. Astronomers have found evidence of planets, or at least the remnants of planets around white dwarfs. In some cases, they've detected heavy elements like calcium, magnesium, and iron in the white dwarf's atmosphere. Elements that shouldn't be there, because white dwarfs are supposed to have pure hydrogen or helium atmospheres. The explanation is that these elements are coming from destroyed planets. Specifically, from rocky planets or asteroids that got too close to the white dwarf, were torn apart by tidal forces, and then accreted onto the white dwarf's surface. This process, called planetary accretion, is thought to be common around white dwarfs, and it's a direct consequence of the Sun's or any star's mass loss. Here's how it works. During the red giant phase, as the star loses mass, the planet's orbits become less stable. If there are multiple planets, their gravitational interactions can become more chaotic. Planets that were once in stable, well-separated orbits can start to interact more strongly. In some cases, this leads to close encounters. One planet's orbit might get perturbed, sending it on a trajectory that crosses the orbit of another planet. Eventually, the two planets might collide, or one might get ejected from the system entirely, leaving the other in a highly eccentric orbit. If a planet ends up in a very eccentric orbit around a white dwarf, it can pass close enough to the white dwarf that tidal forces tear it apart. The debris forms a disk around the white dwarf, and over time, that debris spirals inward and gets accreted onto the white dwarf's surface. Astronomers have observed this process in action. They've detected circumstellar disks around white dwarfs. They've measured the composition of those disks and found that they match the composition of rocky planets, and they've tracked the rate at which material is being accreted onto the white dwarfs. All of this is consistent with the idea that planetary systems can become dynamically unstable during the mass loss phase, and that some planets end up being destroyed as a result. This is another reason why understanding the Sun's mass loss rate is important, because it tells us something about the long-term fate of planetary systems, not just our own, but planetary systems around other stars. And it raises a final question. If stellar mass loss can destabilize planetary systems, could it also create new configurations? Could planets that were once in close orbits be pushed outward into regions where they might become habitable? This is speculative, but it's a possibility. And it's one that astronomers are beginning to explore. For all our precision, there are still things we don't understand. We don't know exactly how the solar wind is generated. We know it comes from the Sun's corona. We know it's accelerated by some combination of thermal pressure and magnetic forces, but the exact mechanism is still debated. The Parker Solar Probe is helping to answer this question. By diving through the corona, it's measuring the solar wind at its source. And the data is surprising. The solar wind is more turbulent, more variable, and more complex than models predicted. There are structures called switchbacks, sudden reversals in the direction of the magnetic field embedded in the solar wind. There are jets of plasma shooting out from the Sun's surface at speeds of hundreds of kilometers per second. And there are waves, Alfvén waves, named after physicist Hannes Alfvén, that transport energy from the Sun's interior to the corona. All of these features affect the solar wind's mass loss rate, but we don't yet understand how they all fit together, or how they vary over the solar cycle, or how they might have been different in the Sun's past. We also don't know if there are other processes contributing to the Sun's mass balance. Exotic processes, things we haven't thought of yet. For example, some theories predict that the Sun's core might be producing dark matter particles. If those particles are escaping from the Sun, they would carry energy and therefore mass with them. The rate would be extremely small, but over billions of years, it could add up. Or consider neutrinos. The Sun produces trillions of neutrinos every second as a byproduct of nuclear fusion. Those neutrinos carry energy. But unlike photons, neutrinos barely interact with matter. They pass through the Sun and through the Earth, almost as if nothing is there. Because neutrinos carry energy, they also carry an equivalent amount of mass. And that mass is being lost from the Sunday. The rate is tiny, about 2% of the radiative mass loss. But it's there, and it's already accounted for in the theoretical calculations. But what if there are other particles we haven't discovered yet? If the Sun is producing them, and they're escaping, they could contribute to the mass loss in ways we haven't measured. This is speculative. But it's a reminder that our understanding of the Sun and of physics in general is incomplete. But there's a deeper question here, a question that goes beyond the Sun's mass loss. Why does the universe work the way it does? Why is the gravitational constant constant? Why do stars lose mass? Why does general relativity describe gravity so accurately? These are not questions that have easy answers. They're questions that push at the boundaries of our knowledge, questions that remind us how much we still don't understand. The measurement of the Sun's mass loss rate is not just about the Sunday. It's a test of our understanding of physics, a test of general relativity, a test of our models of stellar evolution, and a test of our ability to make precise measurements of the universe around us. So far, everything is consistent. General relativity holds. The models work, the measurements agree, but there are still uncertainties, and those uncertainties leave room for something new, something we haven't discovered yet.